Should start soon. Yep, you are recording, and I move over to the screen. And hopefully everything going well. It should be all right. We've never been told how to. None of your data made sense. Well, but that's an interesting observation, isn't it? If it doesn't make sense, then obviously there is something interesting going on. So either there is an issue with the data analysis, which of course can happen, or your experiment showed something very different to what you originally had planned, and that is definitely worth discussing. Yeah, I think that's a very good advice about the BI 400. That's the academic advisor page, isn't it? Oh no, Mokam. The last lecture is in 2 weeks' time. You don't have holidays yet. No, it is the last lecture that would be, that could be sort of face to face. But from basically today, then onwards, all lectures at the university, including practicals, will be shifted to online. That's probably what it says. For kinetics, I've planned the next 2 weeks for kinetics up to Christmas. Oh, I think what I'm going to do is, because I understand that kinetics is not everybody's cup of tea, I will give you some additional exercises for that. So I'm sure you you will, without any doubt, you are smart enough to understand that stuff. So don't worry. Well, you get a lot of exercises for this module, practice calculations on the website, where there are video tutorials. So these asynchronous tutorials, you have them. Yeah, well, you need to get used to that, because we will do a lot with that next term when we talk about metabolism. Okay, thank you, Rian. I'll see if I can do more of these Google Docs. But now let's get started, because the sooner we get this behind us, the sooner we can finish and I can have my obligatory Friday afternoon nap. Please don't forget to register your attendance on Moodle, and Bernardo has kindly provided the link, and I'm sure he will put it up again. Thank you. It works. So what I want to do with you today is I want to show you how we can find a rate constant and rate order when we look at a reaction. And I will answer your question next week, Daria. So don't worry. It's neither. But there is something special about this test. So don't worry about the test, right? Okay, so yesterday we started with an introduction to this kinetics. And we said, for example, we have a reaction where we have a reactant or substrate. And this is consumed in a reaction like that. And I indicated like that. I'm not necessarily writing a product or B or something like illustrate this, that we are talking about the consumption of A, and A disappears and is converted into whatever. And we said we can write the general rate law or rate equation. And we said the change in the concentration of A per time unit, and the little d's indicate that the units are really, really tiny, tiny, tiny. So these changes are minute that we are looking at. These so this change in concentration over change in time, that is our rate of the reaction. And if we look at a consumption of it, the rate is negative, which we indicate with a negative sign. Negative K times concentration of A to the power of M. And we said this K is the rate constant. And the M, that was the rate order of the reaction. And that in general is really the rate equation. And that's something that I think is not terribly difficult to understand. What we haven't looked at yesterday was the units for these different things. And obviously, you know me, I'm quite keen on units. So let's just simply go through the units for things in a systematic way. So first of all, what would be the unit for A in the way I write it? What is this A in these brackets? What does that represent? What is A in bracket? Absolutely right. Yeah, it is a concentration. So here the unit would be concentration. And I just leave it like that as a sort of general as possible. It could be mole per decimeter cubic, or mole per liter, or millimole per liter, or whatever. Well, just let's call it concentration. What is the unit for this dt? What is this T? Seconds, or in general, what could it be? More general, seconds, you're absolutely right. I just write it as time. So this could be seconds, minutes, years, decades, whatever. And concentration, we said it could be molar, it could be per liter, it could be is concentration. Right, so, or hours, or whatever for dt. So on the left side of the equation, we have concentration over time. And this is actually what I'm showing you here, is a really neat trick to check concentrations and to check units and find units, because we can set up what is called a unit equation. So we have equals negative k times, so we set the A in bracket, again, is concentration, to the power of m. And if we take anything to the power, then this usually would have no unit. So now we need to find out what is the unit for K. Unit for K. And the way we can do that is we just simply solve this equation for K. We don't even bother about this negative sign, because that wouldn't change the units. So what we can do is we can do K, the unit for K, equals concentration divided by time. We bring that to this side, times concentration to the power of m. Or we can simplify that. We can write this as concentration to the power of 1 minus m divided by time. So that's the unit for K. And what we see is it really depends on this rate order. Well, I can write concentration divided by concentration to the power of m. I can write this as concentration to the power of 1 minus m. That's just simple, how shall I say, algebra. Yep. Okay, good. Now, the unit for K really depends on the rate order. So unit of K depends on rate order M. So we also said yesterday, M can be any number. Can be any number. whole number, fraction, irrational number, positive number, negative number, can even be 0. And a big question is, how do we find this m? And there is a very, very simple trick to find m. We just use our rate equation, where we just simply write rate of the reaction equals negative k times concentration of A to the power of m. And in order for this trick to work, what we need to do is we need to be a little bit, how shall I say, dirty. We play dirty. And what we do is, instead of saying we are looking at a rate, we are looking, without telling anyone, we are looking in reality at speed. So what's the difference between the rate and the speed generally? What did we say yesterday? The minus k is when we are looking at the consumption of something. That's where the minus is coming from. What's the difference between the rate and the speed? Yeah. And in terms of sign, we said speed is always positive, whereas the rate can be positive or it can be negative. And in this case, when we're looking at the consumption of this reactant of A, when we're looking at that, the rate would be negative. And because the speed is not directional, we always treat that as something positive, as a positive thing. Rate can be both positive or negative, but the speed would be always positive. So what we can do is we can just simply say the speed of the reaction, or we can simply say the rate of the reaction. And this time, what we do is we write it like that. And these vertical lines indicate that we're taking the absolute value. The absolute value. That means the absolute value is always positive. So in this case, we use just simply the positive rate. Although we know that the rate is negative, but in order to find the rate order, we need to take the positive thing. So we'll just simply say then k times a to the power of m. And now we want to find m. Do we find an exponent? How can we organize that? What mathematical trick can we do? Any ideas? Yes, absolutely right. What we can do is brilliant. Great idea. What we can do is we can take both sides log, and we can take actually any log that we want. It can be log to the base of 10 or the natural logarithm ln, whatever you want, it works either way. because the rules of logarithms in this case don't depend on the base of the logarithm. Let's just take log to the base of 10. So what have we got? We have log rate and I write it like that. No, log, it is actually log is the best thing that can happen to you because it makes life so much easier. Trust me on that. Trust me, I'm a doctor. Equals log k times a to the power of m. And I've written that just simply in these brackets. And again, that is log 10. I will forget to write that, the 10 all the time, so forgive me. So if you see log, then this usually means log to the power to the base of 10. Now we can simplify this part here. We can simplify this to log k. And how does a multiplication change inside a log? What happens to this times here? Absolutely right. It turns into a plus. Plus log of, what have I got left? Concentration of A to the power of M. Now I can even further work with this one here, log of A to the power of M, because I can write this as M and it's a very good question, but I show you what you can do with that. M times log of concentration A. So what have I got? I've got log rate equals log K plus M log concentration of A. Okay, so that is what my rate equation looks like when I log it. And let me just simply write this in a slightly different format. Log rate equals M log A plus log K. Okay. What have I gained from that? Can anyone see what this equation actually shows me? What is this? Y equals mx plus c. It is, yes, it is the equation for a straight line. Look at that. Y equals mx plus c. Does that make sense? It's the equation for a straight line, and we can work with straight lines. So we can actually find m, because m is the gradient, of the straight line, and our intercept here would be log k. So let's just simply try to illustrate that, what it would look like. On the x-axis, we would plot, what do we plot on the x-axis? Absolutely right. We would plot log concentration of A. And on the y-axis, we would plot log of our rate. What are the units for log A and log rate? What units would we use? What units do they have, log A and log rate? Concentration, nice try. I like your answer, but it's not the right one. Molarity and seconds. Again, it's a nice answer, but it's not the right one. Reynolds, you are absolutely right. Logs have no units. When you log something, it automatically, by default, loses the unit. So no unit and no unit here. So we cannot have any units when we log something. So these are the very rare occasions where you get away without putting any units down. So what do we get? We would get something like a straight line. Something like that. When we do this, when we take, for example, different concentrations of A and take the log of these different concentrations, and then we measure the rate. In this case, we measure the log rate of that. So here, the gradient of this line, this gradient here would be our m, the rate order. That's the rate order. Now, what about our k, our rate constant? How do we find the rate constant? So we just extend and find the y-intercept. The y-intercept. What is this y-intercept? What is this point here? It is, indeed, it is log k. It's not k, it is log k. And that's very important, okay? It's log k, not k. But it's easy to convert log k into k. All we need to do is k equals 10 to the power of this value of this log k. value. You can do it with the natural logarithm with ln, but then you would all your things would change from log 10 would be ln. Here you would have ln, and here this would also be ln. Whichever logarithm you use, it doesn't matter, but you need to be consistent. You can't switch them. Now, I've drawn it into some here in a way that some people find causing problems, because what they say is, wait a moment, the y-intercept here is negative, right? This here is a negative value, for example. Y-intercept is negative. What about k? Can k be negative? Can the rate constant be negative? What did I tell you yesterday? Did I actually say that the rate constant can be negative? Thank God for that. The rate constant can only be positive. But I get a negative y-intercept here. K is always positive, absolutely right. But I get a y-intercept that is negative here. How do you explain that? The y-intercept is negative, but I told you k can only be positive. How do we reconcile that with each other? It is log k, exactly. We don't have k here, we have log k. And log k can be a negative number. It can be, it doesn't have to be, but it can be a negative number. K itself is still a positive number. So even if you get a negative log k, it's not a problem because k is still a positive number. Okay? So let's just simply do a very simple sort of, well, almost experiment. Let's say we have a rate and we have, for our consumption of A, rate equals minus k times A to the power of m. So this is again, this is the general rate law for that. Now let's say we calculate the rate if we have m, let's say m equals 1. This reaction would be called a first order reaction. And that's a very, very common reaction type. It's a first order reaction. And first order because m equals 1. Just a quick question. How would you write a zero order reaction? What's a zero order reaction? What do you think? In a zero order reaction, what would be m? You don't have to be a rocket surgeon. It would be a to the power of 0, or, and in this case, m equals 0. Absolutely right. But let's not work with that. We will come to that probably next week. Let's go for m to the power of 1. So, and let's just simply say our rate constant, let's say k equals 0.1 per minute. So we would get the rate equals minus 0.1 times a to the power of 1. Okay, and probably, let me just quickly put this in here, make it nice. 0.1 per minute times a to the power of 1. Okay? Okay, so we said in order to work properly, we take the absolute value, so we don't need to worry about the negative sign. And we have rate equals 0.1 per minute times a to the power of 1. And for a, let's say we take 1 molar concentration. Okay? So what would you get for this reaction? What is the rate in this case? Oh, I just simply, as an example, I put it as 0.1 per minute because that's very easy to calculate. It can be, of course, it can be any other number. I just want to give an example that is easy to calculate. So what is the rate that we get? It is exactly 0.1 molar per minute. Or I can write this as 0.1 molar minute to the minus 1. That's exactly equivalent. Okay, now I look at that and say, what happens if my concentration of A equals 2 molar? What happens to the rate? So the new rate, let's say rate 2, equals, what do I get? Absolutely right. I get 0.2 molar per minute. So what we see is that rate 2 is double the rate of rate 1, if I define this as the rate 1. Okay? So in this case, I doubled the concentration of A, and the rate doubled as well. Okay? So that was quite easy. Let's do another example. Let's say we have, and I come back to Jack's question. Let's have rate equals minus k times a to the power of 2. What would you call this reaction? What would you call it? The second order. Absolutely right. It's a second order reaction. And let's do the same thing. Let's say K equals 0.1. Now we need to be careful with the units because we said earlier for the unit it is, where was it? Let me find this. The unit for the of K is concentration 1 minus m. So we would have 1 minus m per time with the molar. So here our rate constant would be 0.1, let's say molar to the minus 1 per minute. Let's do it like that. So let's say our concentration of A is again 1 molar. What would I get for the rate? If I've got K 0.1, and let's just simply ignore this minus here, what would I get for my rate 1? Absolutely right. I get 0.1 per molar times a minute. That's the rate constant times 1 molar squared here. So 1 molar cancels out and my rate would be 0.1 molar per minute. Okay? Are you happy with that? Okay, now what I do now is I do exactly the same as I've done here. I now change my rate. I change my concentration and I say A equals 2 molar. So I get my rate 2 equals 0.1 per molar and minute times A to the power of 2. Yep, I can put up some questions for that. So tell me, what is our new rate? What is rate 2? Ah, look at that. We have 0.1 per molar times minute times 2 molar squared. And that, of course, gives me 4 molar squared. So my rate 2 equals 0.4 molar per minute. So my new rate, rate 2, is actually 4 times the rate. Rate 2 is 4 times the rate of 1 when A gets doubled. Do you see that? So I double A, but my rate increases by factor 4. And why is that? Because I've got a second order rate. Does that make sense? So in the case of a second order, when we double the concentration of A, the rate quadruples. What would happen? What would happen if I have this second order rate and I change my concentration of A to, say, 3 molar? What happens? No, we don't have a problem, because Benjamin and Mogham already gave the answer. Look, we have our new rate 3 equals K. That was 0.1 per molar and minute times A to the power of 2. And in this case, we have this one here, 3 molar. So we have 0.1 times 3 molar squared. And that gives us 0.9 molar per minute. And while my rate 1 was 0.1 molar per minute, my rate 3 is rate 3 equals 9 times rate 1. So it's not 16-fold, it's 9 times the rate. Does that make sense? So if you have a very simple reaction, you can actually figure out what is the rate order just by simply doubling the concentration of A. If you double the concentration of A and your rate doubles, you know you have a first order. If your rate quadruples, you know you have a second order reaction. And of course, then it gets more interesting. Absolutely right. If you have a second order reaction. So the rate is the square of the concentration. The rate is the square of the concentration if you have a second order reaction and you have a sort of an additional factor in it. Now, what would happen if you were working with a third order reaction? If you're working with a third order reaction and you doubled the concentration of A. What would happen in this case? How much does the new rate change? And with that, I leave you to it. A little bit of brain jogging. You can post your comments in the chat box, but I'm not going to say anything. Let's see whether you can work it out yourself. Have a lovely weekend. Enjoy yourself. And I will see if I can set up a few additional questions for you guys. See you next week. Be good. Don't do anything I wouldn't do.